Hello everyone, welcome back to another class of fundamentals of particle and fluid solid processing. Till last class we have seen the fundamentals of sedimentation, its different mode during this process, that is the batch settling and the continuous operation. We will continue with this idea that we ended in the last class, that or the concept that in continuous operation how these concentrations at any axial position from a vertical distance from the top or from the bottom, that can be measured. So, we started with this concept of this thickener, that equipment that is used for sedimentation. Now, we have seen its working principle, and the reason that earlier we have studied that why there was derivation for expression of flask for net upward as well as the downward flow. Okay. So, because in thickener we can have two zone basically. So, in practice we have this off-flow condition where the clarified liquid are flowing and is taken out from the vessel called the overflow, and the downward motion of the solid particles or the downflow region where the solid particles settles. There is a stirrer that moves, and the utility of this stirrer we have seen earlier, or we have discussed earlier, that it actually reduces the apparent viscosity of the suspension. It moves at a very slow pace, and what happens, it actually scraps these sedimented materials that falls on this bottom of the surface. It collects, it helps to collect those sedimented particles which are taken out from the vessel at certain point of time, or can be regularly or continuously. And the this thickened liquid, the whole thing, that basically goes out from the bottom of the liquid, this vessel, as the thickened liquid outlet, or we call the underflow. So, and another vital thing is that this feed that comes here is not just left at the top surface of this vessel or the pool of liquid. Okay. It actually comes down a bit, that is a certain depth from the top surface of the vessel, and it is introduced in a possibly less turbulent manner. Now, as I mentioned that this thickener has twofold objectives. One is to produce the clarified liquid, the overflow, as clear liquid as possible, and the other is creating thickening suspension of the suspension. Now, to produce this clarified liquid, we typically we have to focus on the diameter of the vessel, because at this section the liquid upward velocity has to be lesser than the particle settling velocity. The design parameter of this diameter has to be such that this liquid upward velocity should be lesser than the particle settling velocity for the corresponding feed, or the feed rate that we are introducing. So, which means the diameter of the tank is of considerable importance or considerable consideration in this case. Now, for the downflow region, to create the thickening of the suspension, that means which depends on the particle residence time, okay, the depth below the feed inlet is what that is important, because from here the feed is given or provided, and then the particles travels this distance. In ideal case, when all the particles settles, you have a clear liquid zone that we have discussed earlier, and that liquid is withdrawn from the overflow. So, since in a real thickener we have these two zones, that is, one is the upflow zone and the other is the downflow zone. And the upflow, that is above, the point is this above this feed inlet or the feed well, and the other region is below this feed nozzle or the feed well. So, if we consider that the feed rate is at F, the volumetric feed rate, the corresponding concentration of the feed is of Cf, which is introduced at this point, okay, at a certain depth from the top of the vessel. Then say we have the overflow volumetric flow rate of V and the underflow we have L. The corresponding concentration is Cl and Cv, like here we have Cf. Okay. Now, as I mentioned that there is basically two zones in a real thickener, one exactly below the feed nozzle or the feed well. Say it has a mean particle concentration of Cb, and on the upflow zone, say we have the mean particle concentration of Ct. For the sake of understanding, you can remember the T here is for the top portion, B for the bottom portion. Okay. Cv is for the overflow, Cl for the underflow. Now, the material balance over the thickener, for overall material balance as well as the particle balance, we can have these two expressions, that is the total flow is equals to the overflow plus the underflow, that is the feed is equals to overflow plus underflow, and the particle concentration is FCF is equals to volumetric flow rate of the overflow multiplied by the corresponding concentration plus the volumetric flow rate at the underflow with its concentration. So, these two expressions, okay, these two expressions actually now can be linked with this total continuous flash plot for the upflow and downflow sections in the thickener. So, this, if we go into details, we will see that these two expressions combines this total flash plot for the upflow and the downflow sections in the thickener. Now, how that happens? Say we have, this is the below feed section, which is of immediate importance. The particles are settling in that zone. So, this is the, say, below feed. Now, this is the, say, this we have, say this is the batch flask data. This is the concentration in the x direction, and y direction we have the volumetric flask. Okay. Now, which means this F by A, V by A and L by A, okay, these slopes, okay, these are the value of slopes of the bulk flow rate, of the underflow and the overflow. So, in this case, so this line, say, is having a slope of L by A with the underflow. okay, and this is the F by A slope starting from this 0 point. And then, like we have seen earlier, that the settling rate, that the batch settling flask plus the bulk gives us the downward flask of the this suspension below the feed, which say the resultant is this one. Now, this F by A, physically what it means, it represents the relationship between the feed concentration and the feed flask for the volumetric feed rate F. When the total flask in the upflow section is 0, again you remember the thickener geometry. So, if feed is fed at a depth of this distance, you have upflow in this zone and you have downflow in this zone. So, when the total flask in the upflow section is 0, then this F by A, the line with this slope, intersect this total curve, total flask curve, okay. This intersect with the curve for total flask in the downflow region, which means this point intersection is basically tells us that this is a critical value where if you operate that, the thickener with this concentration and this flask rate, there would be no upward or say the flow net total flask in the upflow section. In this section, there would be no flask in the upflow section, which means this is a critical value beyond which or above which the thickener will be overloaded. There will be the particles that would flow in the upward section as well. Or if it operates a value below this one, then it would operate in underflow condition, or let us say the underloaded condition. All the flask will be in the downflow section. So, let me iterate once again. For a real thickener, once we have this batch settling data and the bulk flow rate, what we can do? We can draw this F by L, which is the feed flow rate by A, the area of cross section. So, F by A and L by A as well as the V by A. Now, the V by A is happening as a upward flow. So, in this case, as we are considering these are having the positive slope, that would have in the negative direction, which would be look like this kind of a scenario, that and the below this is the above feed scenario, okay. So, the downward flask above the feed would be something like this, because here we have the overflow flask that is having a line with a slope minus V by A, because the overflow flow rate is V. So, here the overflow flask line will have a slope of minus V by A, okay, and it would not cross anywhere in this total flask above the feed, which is the downward flask above the feed. This line is the downward flask above the feed. So, this is the batch flask data. We have the F by A and L by A line. This is the resultant total flask, that is downward below the feed. The point where this intersects, the point indicates that there is no upflow, which means that is a critical point at which, or the critical condition at which the thickener can operate. So, we say that this is a critically loaded thickener, and at that position this Cf, or the feed concentration, is actually the overall bottom mean composition, which is Cb. Now, the point, as I mentioned, that it intersects the y axis at a value UPS, which is the critical flask. At that critical flask, if we extrapolate this line, it intersects this L by A curve at a point, and that point indicates that what would be our underflow concentration. So, for critically loaded thickeners, when we have this concentration, we know from the intersection between the F by A slope line and the total flask line. From there we can have this critical flask. This critical flask line, where it intersects with the L by A slope line, that concentration is the concentration of the underflow. And the overflow condition, that means, now since this is the critically loaded scenario, that means all the flow is happening, or all the particles settling is in the downward motion or in the downflow zone. There is no particle in the upflow or upflow region, and that is why Cv is basically 0. There is no other solution for Cv from this graph. So, I hope you have got this point, because this is the critically loaded scenario, the critical point where the thickener is working. Now, critical means there is no flask or no particle flask in the upflow section. Total flask in the upflow section is 0. At that point, this line of F by A intersects this total curve at a certain point. That is our critical condition, or the critical concentration of the feed, and the corresponding flask is the critical flask. At that critical flask, the line where it intersects the straight line with the slope of L by A, that gives us the concentration of the underflow, and this is the line having a slope of minus V by A, which is above the feed, which is the upflow region. Here we find the solution for Cv is only one possibility, that is Cv is equals to 0. So, which means that in underloaded condition, or the underloaded condition, what would happen? So, this is our downward flask below the feed. Okay. This is F by A line, this is L by A line. this is actually the critical point, but say our thickener is operating with the Cf this value, which means it is operating below the critical region or the critical limit, which is, that means there definitely would not be any net flow in the upflow region. Total flask in the upflow region is 0. So, the corresponding concentration at the downflow or the underflow would be the intersection between this line and the line with the slope of L by A. This would be our CL, and all the flow is happening in the downflow region. This can also be seen from here that the only possibility of this solution for CV is the 0. So, in underloaded condition, everything is happening in the downflow region. So, what happens when this is overloaded condition? So, the overloaded condition, by this we mean that, again if we draw those curves, that this is the downward flask below the feed total flask, this is a line with slope L by A, this is the line with slope F by A, which means our critical point is this one. But say the thickener is operating with a Cf that is in excess of that, which means the scenario is overloaded. Now, what happens once this is overloaded? We can see that actually for that condition the bulk flow rate is basically this one, which is the UPS corresponding to this line, but critically it can handle this value, which is LCL by L, that is the maximum possibility it can handle. Clear? Which means the intersection of this critical line this F by A line and the total flask gives the critical point, but we see that the thickener is working with the concentration at the feed in excess of that, in excess of this Cf, this critical, say if I say Cr, if this is the concentration critical, then say this is the Cf it is operating, which is in excess of that. So, this Cf actually correspond, because F by A line represents the relation between the flask and its corresponding concentration. So, if the concentration is this one, that means the feed flask is this one, this value, but the thickener can handle this critical condition. Critical condition means again the condition where the total flask in the upward section is 0. Now, it is overshooting that value, which means now there will be some excess flow which will go in the upward section, because in underflow condition there will not be any flow in the upward section or the upflow section. But in overloaded case, this would be the excess flow rate that it can handle in critical condition, which this value, okay, if we plot for the above feed scenario, it would again cross this L minus V by A line at a certain value and the total flask at a certain concentration. Now, the point where it intersects this total curve, total flask, this concentration is the CT, which is the mean concentration at the top section. Okay. And the line it intersect with the V by A line, the point where it intersect this one, this is CV, which is the concentration in the overflow. Okay. So, this is the concentration in the overflow, this is the concentration or the mean concentration in the top section. And here similarly, like the previous one, in the line corresponding to the critical flask that it intersect with this L by A line, that is the concentration of CL, that is the underflow concentration. So, which means we can have all the necessary concentration values if we can have this plot or such information. So, how these informations are useful? Say we have a problem that using the batch flask plot given in the following table, in the next slide I have that table, graphically determine the limiting feed concentration of a thickener that has a cross sectional area of 300 meter square, handling a feed rate 0.03 meter cube per second with an underflow rate of 0.015 meter cube per second. So, which means for a thickener area, cross sectional area is given, feed rate is given, okay, underflow rate is given. We have to determine the underflow concentration and overflow concentration under this condition. This is the first part. So, how should we solve this? First of all, this is F, this is L, this value is known. So, we can easily calculate what is V, which is F minus L. Okay. And then we can find out what are the values of F by A, L by A and V by A, or rather minus V by A. Then what would happen? We have this data given, that is the C, this is the flask. So, C and this is the flask, UPS is mentioned. If we plot this, say we have a plot like this. Okay. So, this is for the batch settling curve, like this one that we had here. Say we have got a plot like this. Then what we do? We have to draw this L by A and F by A line. This is the L by A and this is the this is the F by A and this is the L by A line, or these are basically the slope. F by A line means the slope having F by A and the slope having L by A value. Once we have that, the point where after that what we do, we add this batch flask data with this L by A data, because the total flask, okay, at any point is basically the settling flask plus this underflow concentration or the underflow flask. By doing that, we get this curve. This is the total flask plot. Once we have it, then we will see that the point of intersection of F by A line and this total flask, that is the critical concentration. The point, the x axis corresponding to that intersection point is our critical point or the critical concentration that the thickener can operate, beyond which there will be total flask or the flask in the upflow zone. The line, the straight line that corresponds to this critical flask and where it intersects with this L by A line will give us the concentration of Cl or the concentration at the bottom of this underflow condition. And similarly here we can have, since we can then see whether that concentration is basically beyond or below the critical limit. If it is below critical limit, then the concentration of V or the overflow would definitely be 0. The second part asks that under same flow condition, if the concentration of feed increases 110% of the limiting value, which means we are overloading that. In that case, what would be the solids concentration in the thickener on overflow as well as in the underflow? So again, in this case, once we have that, then see this scenario becomes much easier. So once we have found out, say this is the critical point and our current operating point is 110% extra than the critical limit, we draw this line once again and we find out what is the actual flask, what is the difference between the actual flask and the critical flask, and that one is added at the bottom of this or say above the feed this flask condition, and we find out the corresponding V, Cv and the mean concentration at the top region. So this is how we use this information, or if the problem is given in such a way, this graph or this information, these graphs are helpful in calculating those concentrations. So for any thickener problem, I hope you should be able to find out that what are the concentrations below the feed depth, above the feed depth, at its critical operating concentration, provided the sufficient information are given like the batch settling data, the flow rate, the concentration of the flow rate, the feed rate. Okay. So with this we will come to end of this section, that is the separation of solids from fluid by means of sedimentation. In the next class we will be coming up with the other section, and until then I thank you for your attention and listening to this.